Good morning, everybody. I hope you're having a wonderful Tuesday. Today, I hope to wrap up our discussion on incompressible flow and start our discussion on compressible flow. I figured it would probably be helpful to do a quick recap on friction and incompressible flow, followed by a couple example problems, and then start discussing our main content for the week, that being compressible flow and frictional dissipation and compressible flow. So last week, we spent our time talking about incompressible flow and friction and incompressible flow. And we identified when analyzing flow systems for power and energy requirements, we can consider our mechanical energy balance and specifically how friction can be incorporated. And we learned that friction can be considered one of 4 different categories. We have skin friction due to shear stress exerted by the solid fluid interfaces. Then we have expansion losses, contraction losses, and fitting losses, all a function of the kinetic energy of the system. Thus, we can describe our full friction term by the following expression: 4F L over D plus KE plus KC plus KF, all times U squared over 2. And with that, we can then finally fully solve our mechanical energy balance, now incorporating frictional dissipation. So let's work an example together to kind of further exemplify this. Water. For this example, we have water being pumped from a reservoir from the top of the hill through a 6-inch Schedule 80 pipe at an average velocity of 2.2 feet per second. If the pipe discharges at a level of 330 feet above the level of the reservoir, assuming the pipeline itself is 1,100 feet long, the question asks if the overall efficiency of the pump driving the flow is 70% and the cost of electricity is 7 cents per kilowatt hour, what is the hourly energy cost for pumping the water? So this one has quite a lot of moving parts. So I'll give you a few seconds to jot down any notes you'd like, and then we'll start to jump in. Okay. So for this example, we have water being pumped uphill. The velocity was approximately 2.2 feet per second. The pipe diameter, it was a 6-inch Schedule 80 pipe, which from our Appendix 3 tells us that the pipe diameter is 0.576, 0.5761 feet. Actually, no, I'm wrong. I mean, that didn't sound right. 5.761 inches, which should be about 0.48 feet, which means our flow area from our table is 0.181 square feet. From the problem statement, it also tells us that our delta Z, or elevation gain, is 330 feet. And the flow length is 1,100 feet. So in this system, first thing I would do is write out my mechanical energy balance. Then I can ask myself, what can we neglect? The problem statement didn't say any in terms of net pressure gain, so I would say P1 is equal to P2. I have friction, I have work, and I'm probably going to have to consider my velocity head. And so I would say U2 minus U1 squared over 2 plus G times Z2 minus Z1 plus work plus friction equals 0. I would set my initial velocity to 0 and my initial height to 0. This would be my 330 feet, and this would be my 2.2 feet per second. So the only thing that I'm missing to solve for my work is my frictional dissipation. Now, the problem didn't say anything about expansion, contraction, or fittings, so I'm going to assume for this problem that the only friction I have to worry about is frictional dissipation. So my expression for my skin friction in this case would be 2FU squared L over D, which means I need to determine my friction factor. Thus, what I need to do next is solve for my Reynolds number to identify if it's laminar or turbulent flow. So if I do that, the density of water is 62.4 pound mass per cubic feet. The velocity was 2.2 feet per second. The diameter was 0.48 feet. And the viscosity of water, 6.72 times 10 to the minus 4 pound mass per feet second. I do that, I get a Reynolds number approximately 98,000, which tells me it's turbulent flow. So I need my relative roughness factor. For this problem, I'm going to assume that I have stainless steel, where my K value is 0.0015 feet. So my K over D value is going to be 0.0015 over 0.48 feet, which gives me a K over D value of approximately 0.0003. So going back to my friction factor chart, I'm looking for 0.0003 and approximately 100,000, 98,000. So my Reynolds numbers, this is the 10,000s, this is the 100,000, so I'm looking right here. So I have to intersect between 0.003, which is between these two lines, and 100,000, which would be approximately here, or about 0.0048. So from my chart, F is about 0.0048. Now that I have that friction factor, I can then solve for my frictional dissipation, my F, which is 2F L U squared over D, or 2 times 0.0048 times my length, 1,100 feet, times my U squared, 2.2 feet per second squared, divided by my diameter, 0.48 feet. And what I should be left with, which I am, is feet squared per second squared. And I have 106.5 feet squared per second squared for my frictional dissipation term. Now that I have that value, I can plug in my original mechanical energy balance and solve for my work, which is going to be 2.2 feet per second squared over 2 plus 32.2 feet per second squared times My height, 330 feet, plus 106.5 feet squared per second squared. All my terms come out proper, and the feet squared per second squared value and what I'm left with is 10,734 feet squared per second, and it's negative because it's work being done on the system. Everyone following along so far? Now that I have my work, I can solve for my power, which is my mass flow rate times work over my efficiency. So my density is 62.4 pound mass per cubic feet. My velocity was 2.2 feet per second. My flow area was 0.181 square feet. I put all that together, I get a mass flow rate in feet per second. I multiply that times my work, 10,734 feet squared per second squared. And I divide that by my efficiency, 0.7. I also have to divide by G sub C, pound mass feet for pound force second squared. That gives me foot pound force per second. And then I can divide by 550 foot pound force per second to get horsepower. I do that and I get approximately 2.15 horsepower. So now I have my power requirements, and then with this, I can convert my horsepower to kilowatt hours, because I know that 1 horsepower is equal to about 0.746 kilowatts, which means my power is also 1.6 kilowatts. And so to estimate my hourly cost, I can say if I have 1.6 kilowatt hours per hour times 7 cents per kilowatt hour, this tells me my hourly cost, which is surprisingly low. So I got approximately 0.112 per kilowatt. So basically 12 cents per hour. Any questions on that? Let me double check that math just real quick. Make sure I didn't miss anything. Yeah, that's what I thought. This is off by a decimal. It should be 21.5, 16 kilowatt hours. I knew that seemed too low for the degree of pumping we're doing. It should be $1.12. So now that I have that. So any questions on that problem? Everyone following it pretty good? Be comfortable doing that on a midterm? Maybe. All right. Then let's keep moving. make sure I'm sharing the right thing. Okay. One of the last things I want to talk about when it comes to incompressible flow is flow through non-circular channels. One of the most often thing you'll see is things like ductwork. And so it's important to understand the implications of flowing in these systems. So if instead of flowing through a pipe that behaves as a circle in terms of cross-sectional area, a lot of times we can consider non-circular systems. And so if I have, let's say, a ductwork that looks like this with some sort of length, some sort of width, actually that should be height. This would be the length. What we can do is we can calculate a hydraulic radius, which is given as the area or the cross-sectional area over the perimeter. And from this, we can calculate what's known as an effective diameter, which is simply 4 times the hydraulic radius, which indicates the effective diameter is 4 times the area over the flow perimeter. Another situation that will occur, particularly as it applies to heat transfer systems and heat exchangers, is if I have flow through an annulus, identified here as the flow area between the two systems. So if I have, let's say, a double pipe heat exchanger, and I'm interested in the flow associated with the annulus, I can calculate my hydraulic radius as a function of the outer diameter minus the inner diameter over 4. So let's look at one example where we're considering the implications of flow through a non-circular system. So in this example, we have a horizontal ventilation duct, 20 feet long and 2 feet square, is to be replaced by a new duct with the dimensions of 2 feet by 4 feet. Due to complications of installing the larger duct, the new duct will end up being 30 feet long. If we can assume the overall pressure drop remains constant in terms of as compared to the old duct and the new duct, by what factor does the airflow rate increase in the new duct? So this example is an illustration of an important concept that we really would talk about in design more than anywhere else. And it's essentially a case comparison. And the effective way is through a technique that is known as base case ratios, which I'll illustrate here in a second. But the beauty of it is I can analyze the system and perform minimal calculations to obtain my solution. So what we're looking at is comparing two ductworks. This one is 2 feet square by 20 feet long. This one is 2 feet by 4 feet, and it's 30 feet long. Now I can calculate the effective diameter here as 4 times the area over the flow perimeter, which in this case would be 4 times 4 feet squared divided by the perimeter, which is 8 feet, which should be simply 2 feet. However, the effective diameter here should be slightly larger, as we have 4 by 8 feet squared over 12 feet, which gives us 2.67 as our effective diameter. So what we need to do is consider the implications in terms of pressure drop due to skin friction and identify a comparison between these two systems. Well, if I know my friction or pressure drop due to skin friction is 2F rho U squared L over D, I can develop a comparison between case 2 and case 1 and say my delta P2 is 2 times F2 rho 2 U2 squared times L 2 over D2 divided by 2 times F1 rho 1 U1 squared L1 over D1. The first thing I would ask myself is what values can I cancel? Well, the constant I can neglect. If I can assume that my velocity, while changed, may not change the friction factor significantly, I can assume my friction factor is constant. Also, for this system, focusing strictly on the design change, I'm going to assume the density is constant. And what this leaves me with is an expression that looks like this. Delta P2 over delta P1 is equal to U2 L2 times the diameter 1 over U1 L1 times diameter 2. So now I have 3 variables that I have to consider the implications in changing the design that I have here. The most direct way to consider it, since we're interested in knowing the change in flow rate, and knowing that I can solve for flow rate as U times A, which is U times the diameter squared times pi over 4, I can say, well, if flow rate is equal to U pi d squared over 4, that means U is equal to 4 times my flow rate divided by pi d squared. If I do this, I can then sub my 2 flow rates for both my velocity 1 and my velocity 2. So if I do that, I end up with an expression that says delta P2 over delta P1 is equal to 4, and these are supposed to be squared, times V2 over pi D2 squared times L2 times D1 over 4 times V1 over pi D1 squared times L1 times D2, keeping in mind these velocities are squared. Once again, I can ask myself what I can cancel and then distribute these values into my expression. So I'm left with V2 squared times L2 times D1 to the 5th over V1 squared times L1 times D2 to the 5th. And so now I have my change in pressure drop as a function of my flow rate, my pipe, my duct length, and my diameter, and my effective diameters. Now, from the problem statement, they said the pressure drops don't change. So this should be equal to unity if my delta P2 and my delta P1 are the same, which means now if I want to solve for my comparison in flow rates, V2 over V1, I just rearrange my expression and solve. So I end up with L1 d2 to the 5th over L2 d1 to the 5th, all to the square root. And here, now I have, based off the information I was given, an expression for the change in flow rate as a function of the variables which describe it. And I was able to do this with a lot of algebra, but the beauty of it is I didn't need to know any of my values at this point in time. Now what I can do is simply plug in my values. 20 feet, 2.67 feet to the 5th, divided by 30 feet over 2 feet to the 5th. I do this and I have a comparison of my flow rates, V2 over V1. Let's see what I get. I should get approximately 1.68, or my flow rate increases by 68%. So I know that was a little messy and a lot of algebra. Did everyone follow that fairly well? Are there any questions or points that I can further expand upon or reemphasize?
How could you cancel the friction factor? Oh.
No, Mitch, go ahead.
Go ahead, Mitch.
How did you cancel your friction factor? You said the velocity didn't change, but I thought if the area is different, it would change.
I said the velocity is going to change, and the area is going to change. But what I can do in certain cases, now, if I'm honest, these are some assumptions that would probably be best to double check. But if we remember from our friction factor chart, if the flow is sufficiently turbulent, which is usually greater than, when you start approaching 10 to the 7th and beyond, the friction factor ceases to be a function of velocity. So if you get to this region here, and you can, a lot of times you can even consider it, just about 2 million and above, the friction factor isn't going to change appreciably with manipulating your flow rate, so provided you're not decreasing it. And so in that instances, I can say, well, assuming a high Reynolds number, F is constant. And it's a good trick to do when you're looking at base case comparisons. Now, sometimes if you have sufficient information, you can solve for that. But in this problem, I didn't really give you anything in terms of flow rates or actual velocities that you could calculate it. So in this instance, it's just easier and more effective to just assume.
Thanks.
Of course.
Dr. Lopez, I had a question. Could you go back to your OneNote? Because I thought there was something in your notes that I was confused with.
Sure.
Okay.
I'd be happy to go back.
Okay. So, if you scroll a little bit earlier or higher, I should say, where you have delta PS equals U2 L2 D1 over D2 U1 or U1 D2 L1. You first written that down. Okay, never mind. You squared it. Okay, I thought you didn't square it. Never mind. Okay.
Yeah, I originally forgot to square, but then I remembered and corrected it.
Okay, that's fine. That's all I had a question on. Okay. That was it. I thought I missed some math somewhere, but no. Now I see everything's okay. Thank you.
Oh, you're welcome. No problem at all. I completely understand. Any other questions or things that I can further clarify for you? No? All right, well, if not, I guess we can move on. And talk about compressible flow. All right, sorry, just moving some notes around. Any last minute questions on incompressible flow? All right, so the key discrepancy that we have to consider when it comes to compressible versus incompressible flow is that in compressible flow, the density of the fluid is a function of both temperature and pressure. So when I'm looking at flow through a pipe, P1, row 1, P2, row 2, and in this case I have a compressible fluid, I can say that as flow moves through the system, I can anticipate a pressure drop through the system due to shear stress, which results in frictional dissipation. Correct? So what does that do to our density? Anyone?
If it's isothermal, I would think our density would decrease.
So assuming it's isothermal, the density will decrease. You are correct. So what are the implications for that? Well, let's consider it. I'm assuming, looking at our system in terms of our mass balance. Oh, seems like my system had a hiccup. I apologize. Well, from our mass balance, we know that M1 is equal to M2. If I look at a simple flow through a pipe system, where this is kind of my system box. And with that, I can expand and say, well, rho 1, U1, A1 equals rho 2, U2, A2. And for a flow through a constant, cross-sectional area, A1 is equal to B A2, which tells us that our density 1 times velocity 1 equals density 2 times U2. And so the density, as we see it, will decrease due to a decrease in our pressure. We have a pressure drop due to that frictional dissipation. And so since our density decreases, rho 1 is going to be greater than rho 2, our velocity must increase. And I can state that U1 is going to be less than U2. At the same time, I can also state that the product of density and velocity will remain constant. Which we can quantify as a new term known as G, which is a product of density and velocity. You can also think of it in terms of mass flow rate divided by the flow area. And so it has two different terms that you can qualify it, call it the mass velocity, or we can call it the mass flux, because it essentially is the flux of a mass flow rate in a system. And so the important thing to note is that for compressible flow, application of the continuity equation allows us to consider that even though the density is changing, the velocity is changing, the product of these two remains constant. And we quantify that by the mass flux, the mass velocity, and that becomes an extremely important quantity to consider as we discuss and quantify frictional dissipation and energy balance for energy balances, in compressible flow. Now, for low velocity fluids, vapors and gases, compressible fluids can be approximated to behave as incompressible fluids, which means at lower velocities for short distances, you can use the mechanical energy balance as we've been using it to describe incompressible fluids, and you can apply it to vapors and gases with reasonable accuracy. However, when you get to higher velocities, and air quotes here again, Compressible fluids. Behave quite differently. And new expressions must be developed and considered. So to quantify the relative velocity for these systems, we use a dimensionless constant, as we always do, known as our Mach number. And we can quantify the Mach number as a function of our fluid's velocity u over its velocity a at its speed of sound. Keeping in mind the speed of sound for this fluid, a is going to be a function of temperature and pressure. So does anybody have an idea of what the speed of sound is for air? At standard temperature and pressure.
It's like 300 something, right?
It is 300 and something.
Is it 343 meters per second?
You are correct. The speed of sound for air is 343 meters per second, or 1,125 feet per second. So moving pretty quick, if I do say so myself. And for other fluids and air at other temperatures and pressure, we can calculate A as a function of gamma times the fluid's pressure over its density, or application of the ideal gas equation. We can quantify it in terms of its temperature and molecular weight as gamma TR over MW, where gamma is a ratio of the fluid's constant pressure heat capacity over its constant volume heat capacity. And this gamma value is going to be unique to each fluid. So for example, for air, gamma is going to be equal to 1.4. I would just make a note of that because that's going to pop up quite a bit in this section. So with this in mind, and combining our expressions for the speed of sound A with our generic comparison of Mach number, we can say the Mach number can be calculated as rho u squared over gamma times P equals u squared times molecular weight over gamma TR, or if you don't want to have to deal with the squares, you can just handle a square root. So we can use this to identify the Mach number of our fluids. To get an idea of the relative velocity of our fluid as compared to its speed of sound, given its current temperature and pressure. And so doing a quick recap, and then I'll break for some question and discussion. When we're looking at compressible flow, shear stress and frictional dissipation results in an expected pressure drop of our fluid. For a compressible fluid, this has the added implication of a decrease in density of our fluid. By our mass balance and our continuity expression, since the density of our fluid decreases, the velocity of our fluid must increase in order to maintain a stable and constant flow rate for systems at a steady state operation. And thus, we have to consider, since we can approximate quote unquote low velocity fluids, as incompressible fluids and high velocity fluids as behaving with where compressibility becomes an important factor, we have to consider the implications of this system, of these velocity fluctuations. And so we can quantify whether a fluid can be approximated as incompressible or compressible by looking at its Mach number, which is a function of its current velocity relative to the speed of sound. And so, as you can imagine, for fluids with a low Mach number, we can consider them to behave as incompressible fluids. For fluids with a quote-unquote appreciable Mach number, we must consider them as compressible fluids, and that the density and velocity fluctuations will be significant in determining the energy associated with the fluid as it moves through its system. One thing I also want to note is that when a fluid approaches its Mach number such that its velocity becomes the speed of sound, and the Mach number can then be considered 1, this is known as the fluid's asterisk condition. And we denote the properties of the fluid at the asterisk condition using asterisks, because we're very clever. So a property that's given these monikers indicates that that's the pressure, temperature, density, and enthalpy of the fluid at its asterisk condition. All right, so I want to stop here. Is there anything I can further clarify? Am I making sense? Or are you getting a little lost?
I just have a question on the practical applications of using the asterisk conditions. So like, when do we want to use asterisk conditions in like real world settings?
That's something we'll talk about here in a second in terms of the implications of flow at these velocities. Because speaking of, what do we consider flow when the Mach number is less than 1? The Mach number is 1, and the Mach number is greater than 1. Anybody? We can do random pop quiz that's not worth anything. It's like trivia. So flow that is less than 1 is considered subsonic flow. Flow that is equal to 1 is what's known as sonic flow, and flow greater than 1 is known as supersonic flow. There's also a new term that's, when I say new, it's relatively new in terms of the scientific community, where Mach numbers are greater than 3 are considered what's known as hypersonic flow. And that the further complications that arise in supersonic flow change and become so irregular and turbulent that new expressions are derived. So we have subsonic, sonic, supersonic flow, and for those that are interested in, high velocity fluids, as it applies to applications of interest to the military and those sorts, they also consider the implications of hypersonic flow. Any other questions? No? Okay. So when we consider compressible fluids, the three major areas that we're going to discuss in this class are going to fall into, hold on, my computer's getting a little hairy. Isentropic, adiabatic, and isothermal frictional flow. Today we're going to talk about isentropic flow. On Thursday, we'll talk about adiabatic and isothermal flow. So for isentropic flow, this is often referred to as flow through nozzles, primarily because it's one of the only ways in which you can obtain confined sonic and supersonic flow. And so the way these systems are considered and analyzed is following an illustration that I'm showing here. So let's say I have a reservoir and a receiver of gases. So let's say this reservoir is going to be filled with air, and I'm going to flow it through a specialized nodule that looks a little like this. And I'll get my drawing down right. So this nozzle is composed of 3 pipes. We have a converging section, an area of minimal flow diameter known as the throat, and a diverging area. And flow is going to occur from the reservoir of air to the receiver. Now, if I consider a system where the reservoir is at some pressure, P naught, and the receiver is at another pressure, P, I can describe the relative pressures as a pressure ratio, which is given as P over P naught, which is a ratio of the 2 pressures in my system, the air reservoir and the air receiver. Now, if my pressure ratio is 1, that means the pressure of my reservoir and the pressure of my receiver are the same or equal. So what do I expect to happen in terms of flow?
Can you repeat the question, please?
Of course. So in this system, I have a reservoir and a receiver, and I can define the reservoir and the receiver and the pressure ratio, which describes that relative pressure. And if my pressure ratio is unity or 1, that means that the receiver pressure and the reservoir pressure are equal. And for this case in this system, what do we anticipate to happen in terms of flow if my reservoir pressure and my receiver pressure are the same?
Wouldn't it be just subsonic flow?
You could quantify it as subsonic.
Is it incompressible flow?
You could probably quantify it also as incompressible or approximate it as incompressible. So let me rephrase it. If the pressure at both the reservoir and the receiver are the same, what can I anticipate in terms of the flow velocity?
Will the velocity be constant?
Yes. Will my velocity be 0 or greater than 0?
Velocity will be 0.
The velocity will be 0 because the pressure at both the starting point and the end point will be the same. Thus, there is no driving force for flow. Now, what happens if I lower the receiver pressure? So if I lower the receiver pressure, where now my pressure ratio is less than 1. Do I expect my velocity to be 0 or greater than 0?
Your velocity is expected to be greater than 0.
Yeah, so now my velocity will be greater than 0, and I will have flow. Now, initially that velocity will be low, and so the whole system can be considered subsonic. However, in the converging section, as the flow area decreases, I can anticipate that my velocity will start to increase as it approaches the throat. And for a special condition, if I set my pressure ratio to a proper value, the flow will be subsonic throughout the entire converging section and can approach a sonic velocity right at my throat. And I achieve a brief moment of sonic flow. Then it can move on and continue to be subsonic because as the flow area begins to increase again, the velocity will start to fall off. However, if I continue to decrease my receiver pressure, I can further set my system up such that my flow can continue to be sonic even throughout my diverging section. That's funny. Subsonic. Getting hip with the kids. And if I continue to decrease that receiver pressure, I can even regenerate supersonic flow in my diverging section. However, if the flow is not set up properly, I can result in a situation where a further decrease in the receiver pressure results in no change in flow. And so I can quantify that as it's described in figure 6.3 of your textbook on page 141. And what often happens is a system that looks like this, where if I quantify the pressure ratio as a function of the mass flow rate, initially at a pressure ratio of 1, there's no flow. As I start to reduce that pressure ratio, I start to see appreciable mass flow rate. However, over time, I achieve what's known as a constant flow rate. And further changes to my pressure ratio results in no change in flow. And so what this tells me is that there is a maximum possible flow rate for my system. And anything beyond this point does nothing for me. And this is a special condition in compressible flow that we call choked flow. And the implications of choked flow basically means that further increases in our pressure driving force results in no change in our mass flow rate. Choke flow is an extremely important concept when we're considering flow of compressible fluids, primarily because you're in a situation where your driving force is doing nothing for you. And you've essentially, what happens is you're pushing that sonic velocity. Because what happens when you try to achieve sonic flow? Well, in order to achieve sonic flow and sonic velocity, you have to get through the sonic barrier, right? Because at that velocity, the essentially information transmission, the way the molecules will be moving, you end up with, a shock wave that can form in your system. Now, isentropic nozzles are unique in that for a particular design specification, you can have your flow set up that your essentially sonic shock wave propagates along your diverging section such that you never truly experience a shock. However, beyond that specification, you can have a situation where, I can show it, you see this pretty well in figure 6.2. If you're wanting to describe the pressure ratio as a function of the nozzle length, and you can have, let's say, pressure ratios here. And so if this is 1, you can have a system where the pressure ratio falls such that you get appreciable flow, and you get to an area of essentially sonic flow. So you can either get to a point where it just achieves sonic flow, and a point where it continues to be supersonic. So this would be supersonic flow actually, and the line would be sonic flow. And if your receiver is such that the pressure exiting ends up here, you end up with a shock in your system that forces it back into subsonic flow. And so depending on how your system's set up in terms of your relative pressure ratio, outside of the design condition, you can end up with shock waves either in your system, shock waves at the exit, or at the essentially the entrance to your receiver, which is a non-ideal condition. There's only a very particular set of a pressure ratio where you can have stable supersonic flow throughout the entirety of your nozzle. And it's a direct result of the fact that you're trying to essentially achieve supersonic flow within a confined system. And so that wave propagation has to be set such that it follows the diverging section. If there's any sort of discrepancy, you end up with an actual physical shock that forces your flow back into a subsonic state. And so this is a really intriguing and albeit odd concept to grasp in terms of how flow can approach the sonic barrier, achieve a sonic velocity, and even exist as essentially supersonic confined flow. And so any questions, any points I can further clarify? I know this, like I said, this is kind of a strange thing to consider and to grasp. Any questions? I know you have to have questions. This is strange stuff.
Does this only apply to nozzle design or like with the subsonic, supersonic?
In terms of confined flow, it only is possible in an isentropic nozzle. When we consider adiabatic and isothermal systems, the essentially sonic velocity represents the barrier that constitutes choked flow. You're never going to be able to achieve sonic and supersonic flow in typical traditional flow systems. It takes a properly designed nozzle with your pressure conditions at very particular, essentially set points to achieve that sonic and supersonic confined flow. Because in a typical flow through a pipe, there's nowhere for that wave to propagate. And so you're just going to end up with a truly confined flow, and you're going to run up to that mass flow rate issue.
Okay.
Any other questions? All right, well then I have a question for you all to consider. And so, I'm stating that for these flow systems of compressible flow, as we approach the Mach number of 1, we have our choked flow systems, which represents a maximum in our flow rate. And so the question I have for you guys is, how can we design and operate around choke flow? Any thoughts or ideas?
I guess we could find the minimum required pressure ratio to use so that, like, I'm just thinking in terms of economics. We
No, you're
can,
fine.
yeah. So like, however much money it costs to, make that pressure ratio, we can figure out like the least amount of money it would, we could expend by finding the lowest pressure ratio required to get up to that maximum mass flow rate.
All right, so we can identify pressure ratio, which results in confined flow. Here, let me clean up my handwriting. I apologize. All right, I should say choked flow. I don't know. Any other ideas that we can do to move our system out of these conditions?
I just have a question. So in rockets and gas turbines, they usually have these backflow areas right next to the throat that they can like open and close, and it can pull in air, look like circular. Could you use that to like increase or decrease the PR to meet like the specifications you need at different flow rates?
That's probably what it's designed for. It's a way to manipulate the reservoir pressure, because there's no good way if you're in a non-confined flow system, you're not going to be able to really regulate the receiver pressure. So what you're going to be typically rely on is manipulation of your reservoir pressure. And so those design specifications are such that they can tweak the reservoir pressure on the fly in order to basically ensure the stable flow that they want when it comes to sonic and supersonic flow. And whether they want to basically move into sonic, supersonic flow, move back into subsonic flow, and so on and so forth. That's basically their way of manipulating the reservoir pressure. Because the throat, the rocket nozzle design is such that you're not going to be able to manipulate, and you're really not going to want to manipulate the throat's not going to happen. The diverging section maybe a little bit, but the more flexibility you're going to have is in that converging area for the reservoir pressure.
What if we had an expansion tank or something that could hold the force?
No, not necessarily. What I'm getting at is one thing you can do is repressurize your fluid. Because if you repressurize, your density increases. And since the density increases, your velocity will decrease. And you'll move away from that choked flow system. One thing you can also do is minimize your pressure drop. So that means you can ensure there's no appreciable friction, no fouling in your flow systems, no in your pipelines, and you minimize long runs, meaning you're going to be faced often with one or two choices. If you're going to have a long stretch of flow, like a pipeline, right? The national pipeline that supplies most of the fuel that we have in the country, there's only a handful of them. And so you're going to have a couple things depending on if it's a natural gas type pipeline. You're going to have pumping substations at various points to ensure that you can repressurize your fluid so that you don't result in a situation of choked flow. And at the same time, you want to maintain your flow systems, your flow pipelines, so that you don't have unanticipated pressure drop, which is going to push you into that choke flow system. Those, I would say, are the two most common things to consider in order to avoid choked flow from occurring. And I think that's a good place to stop. One thing we're going to look at on Thursday is considerations for frictional dissipation and really looking at what's known as a maximum conduit length. So given an inertial pressure and a fluid's properties, what's the furthest length in terms of that pipeline run that we can go before we anticipate choke flow from occurring? And that gives us a way to calculate, okay, how far apart do pumping substations need to be in order to have proper flow? All right, guys, that's all I have for today. Thank you so much for your attention and attendance. We'll be working on problems in compressible flow on Thursday, as well as the considerations for isothermal and adiabatic frictional flow. But this stuff can get a little weird, so don't feel discouraged if you see some of the equations in this chapter and go, what the heck, this is hieroglyphics again. It can get like that. So we'll talk about it in detail on Thursday. Any last minute questions?
Lucas.
You're welcome. Any other last minute questions or things I can further clarify for you all? If not, you guys have a great rest of your day. Take care. And as always, if you need anything, feel free to reach out.
Thank
Have
you,
a great
Dr.
one.
Lopez.